All right, chemistry cool dudes. Carrying on from our last talk on the oxidation of alcohols, a product of oxidation of alcohols include aldehydes, ketones, and carboxylic acids. And so today's talk, we're going to focus on understanding what these functional groups look like and what they do. So as a summary of last video, here we have I talked about one oxidizing agent, which is potassium dichromate, but potassium permanganate and a few other chemicals can also oxidize chemicals. So what is oxidation? So here I have a primary alcohol, a secondary alcohol, and a tertiary alcohol. What oxidation means in organic chemistry is adding more oxygen into the molecule or more bonds with oxygen. So if you take a look at this carbon here, that primary carbon, it has one bond to an oxygen atom. As we do the oxidation, it now has two bonds, so it's become oxidized. It has more bonds to oxygen. And as that oxidation continues, we have three bonds to oxygen. So each of these products is more oxidized, okay? So a primary alcohol can oxidize all the way to a carboxylic acid, okay? A secondary alcohol would only be able to oxidize to a ketone. It can't go any further. We'll talk about that in a second. And a tertiary alcohol, well, it doesn't oxidize at all. It has no room to oxidize. So as you can see in this, the H, those blue H's are very important. When you're oxidizing, you're removing a hydrogen atom from the molecule. That's what you can see. And that's the simplest way of putting it. But essentially what I'm doing is I'm oxidizing the carbon. I'm changing its oxidation state. And hydrogen is a good source of electrons. So when we're oxidizing, we're removing that carbon-hydrogen bond and giving those electrons away to the dichromate reagent. Okay, so you need to remove a hydrogen atom to be able to oxidize. Here I have two hydrogen atoms, so I can do two oxidations. I have one hydrogen atom, I can do one oxidation. I don't have any hydrogen atoms, I can't do any oxidation. Okay, so now we're going to take a look at the difference between aldehydes, carboxylic acids, and ketones. So in order to separate these products, all right, they all have different properties, they all have different boiling points. As I'm doing this reaction, I will be doing the reaction in a distillation apparatus. Okay, I think you guys have seen that with Mr. Mensa. A distillation apparatus has the reaction here under heat, it's boiling. I have a thermometer to see the temperature of the chemicals that are evaporating. And as the reaction happens, once I've hit the boiling point of a certain chemical being made, that the reaction is not going to change temperature until that chemical has left in a good distillation. Okay, so that chemical as it's being made, if I'm at the boiling point, is going to evaporate, and then it's going to flow through this condenser. The condenser has cold water going in, so it's going to lower the temperature of that gas, condense the fluid into a liquid, which I can then collect. And I'll be monitoring the temperature of that distillation just to make sure that the product that I'm making has the right boiling point. Once the boiling point starts to change, okay, that means I'm making a different chemical. I will change my receiving flask and then start isolating a different chemical. So in this reaction, if I took this primary alcohol and treated it with dichromate and heat, it's going to start to make aldehyde as well as the carboxylic acid. So if I do a really careful distillation, I will be able to isolate some of the aldehyde before it reacts to the carboxylic acid. Okay, so distillation is a good means of separation in organic chemistry. All right, so starting with aldehydes, the general structure of an aldehyde looks like this. This R means any carbon atom or any functional group attached. Not functional group, but any carbon structure attached. Okay, you'll see R a lot in your textbook. Okay, and now the functional group of an aldehyde looks like this. C double bond O bond H. That's the aldehyde functionality. Okay, so if I take a look and see, again, to review the reaction, if I have a primary alcohol and I treat it with dichromate and heat, okay, it's going to remove essentially these two hydrogen atoms to make the aldehyde. Okay, and again, just to repeat, oxidation means increasing the number of carbon oxygen bonds. I went from a single one to two carbon oxygen bonds. Okay, but it doesn't stop there. If I still have that dichromate and heat around, it'll take that aldehyde and convert it all the way to the carboxylic acid, so I have to be careful. Okay, how do we name the aldehydes? Well, the general structure for naming an aldehyde is alkane, okay, the parent carbon chain, alkan, al. Al means that there's an aldehyde functionality in there. So for example, a one carbon structure with a C double bond OH would be called methanal. Okay, a two carbon structure would be called ethanal. Okay, a three carbon structure is propanal. And then here I have a substituted alkyl group. So I'll count 1, 2, 3, 4. Okay, that means it's a bute molecule. And on the third carbon, remember you have to prioritize the functional group. That's carbon 1, carbon 2, carbon 3. So this is 3-methyl butanal. And the properties of aldehydes, they're pretty fragrant. Methanol is a that's formaldehyde. That's what we preserve dead things. Like, for example, in the biology lab, if you see bottles and jars with organisms, they're preserved in methanol. It's a good preservative. It's formalin. Preserve dead bodies in methanol. Okay, so it's a very, very good preservative. Prevents, very toxic. That's why it prevents organisms from growing, like bacteria from growing and destroying the organisms. So you can have jars of brains that have been there for 100 years in formaldehyde because nothing can grow on it. All right. That's basically it. Now this ethanol, that's a product of if you drink alcohol and then your liver is going to process, it's going to start oxidizing the alcohol eventually to acetic acid, which you can then remove from your kidneys. But on the way there, it makes ethanol. And ethanol is not really that polar, so it can cross your brain, the big fatty tissue in your brain, it can cross into your brain, and that's what gives the presence of a hangover. And it's actually very toxic. That's how people get alcohol poisoning. It's not the alcohol, it's the product of ethanol. Basically what you're doing is you're preserving your brain. If you drink too much alcohol, you make that, and it starts to play around with the proteins in your brain. Okay, so you got to be really, 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 really careful when drinking alcohol. All right, and if you have methanol mixed in your alcohol, you're making methanol, which is even more toxic, and that's the problem. All right, that's the one that gets into your brain and causes problems. So drinking methanol would make you go blind and give you brain damage because of that product. Okay, ketones. Ketones are made from secondary alcohols, you can see over here, and they have the general structure where I have a carbon chain over here and a carbon chain over here that are sandwiching that C double bond O. This is the most important part of the structure. If I ever have a C double bond O within the structure that's sandwiched by carbons, that is a ketone, okay? And an example of a good ketone that a lot of girls and guys in the class have used is acetone. Acetone is nail polish remover, okay? So acetone, the real name of it is 2-propanone because this is 1, 2, 3 carbons, and the ketone is on carbon number 2, so 2-propanone. Okay, one is the way we would signal that there's a ketone in the structure. Okay, so how are they made? Again, starting from this secondary alcohol, I treat it with an oxidizing agent. I'll remove those hydrogens, and I will make an oxidized carbon, two carbon oxygen bonds, and that's my ketone. That's acetone. Okay, and how do we name ketones? The ketones are named by adding an "-one" to the end of the parent carbon chain. Okay, so for example, here I have 1, 2, 3, 4, 5, but I should start naming to keep that lowest. 1, 2, 3, 4, 5. That would mean that this is 2-pentanone. 2 because the ketone is on carbon number 2. Okay, here I'll do this again. 1, 2, 3, 4, 5. 5 carbons is the longest chain. 2 is where the C double bond O is, and then on this 4 I have an alkyl group. So this is 4-methyl 2-pentanone. Okay, that's how way we name the ketones. Okay, ketones are also an important part of carbohydrate chemistry. Your body, as it's digesting food or digesting fatty acids, would be making ketones. So if you're in biology, you would have heard of things called keto bodies or the keto diet. Okay, in the Krebs cycle, there's ketones involved. All right, so you'd be hearing that a lot. Okay, carboxylic acids is very common. We've played around with a variety of carboxylic acids in the lab. And that's the final oxidation product, which has a general structure like this, where R is any alkyl group or any parent carbon chain, okay, attached to a C double bond OH. That's the general structure of a carboxylic acid. This is the proton donor, okay? So acids donate protons. That hydrogen would be the acidic proton. Okay, and one big property of carboxylic acids is that they have higher boiling points. Okay, so the carboxylic acid compared to all the products would come off last from the distillation. And the reason for that is because carboxylic acids have very strong hydrogen bonds. If I take a look at the structure, the double bond oxygen is partially negative charged. The hydrogen here, because it's acidic, is partially positively charged. They'll be attracted and they'll form intermolecular hydrogen bonds, okay, from our bonding unit. Okay, so they have very strong intermolecular interactions. They're very polar and they have high boiling points. Okay, they would come off last in the distillation. Okay, the oxidation, to make carboxylic acids, I have to start from a primary alcohol, treat it with dichromate. It's going to eventually go through the aldehyde all the way to the carboxylic acid, which we can see over here. Okay, how do we name it? Carboxylic acids end with oic acid. Alkane is the parent carbon chain. Oic acid represents the C double bond OOH. Okay, so here we have example of meth, that's one carbon, methanoic acid, ethanoic acid, and then here I would have propanoic acid, but there's a substituent here. So this is 2-methyl propanoic acid. Okay, the reactions, the most common reaction that we would see, there's other reactions. I just wanted to present one right now, and then we'll come back a bit later on for the higher levels and present some more. But your body, our organism does reactions with carboxylic acids all the time. Our body actually does this reaction to make fatty acids or fatty esters. We make polymers in our body through carboxylic acids. Proteins are made from carboxylic acids and amines where they polymerize them together. So it's a very, very important functional group in biology. Okay, and this reaction is a very, very important reaction to make biological polymers, for example. And in industry, we use this reaction to make perfumes and artificial flavoring. Okay, so if you take an alcohol, any alcohol, and you react it with a carboxylic acid, in the presence of acid and heat, it's going to form what's called an ester, a functional group called an ester, which we'll show in the next video. Okay, along with the ester, you make water. All right, so a molecule of water is removed from the alcohol and the carboxylic acid when they join these two molecules together to make an ester. Okay, and like I said, esters often have interesting smells and flavors, so we see them in the flavoring industry or the perfume industry is a very common reaction. Okay, so an example of making a perfume and flavor is spearmint. Okay, mint gum that you might be chewing has this chemical in it. So starting with salicylic acid, which is a very important reagent for pain reliever, comes from a tree. Okay, if I take salicylic acid and I react it with methanol, okay, in the presence of acid and heat, it's going to undergo the esterification reaction to make methyl salicylate. You see this hydrogen is replaced with this CH3. Okay, in fact, this OH has been removed and that CH3O has been attached into the molecule to make methyl salicylate. And then all of a sudden, after the reaction, as the reaction's happening, you'll smell a very minty smell appearing. Okay, and you can then isolate and purify the methyl salicylate and use it as flavoring. I don't think it's the best thing to be putting in your mouth all the time, but hey, why not? And then as a product as well, you'll get water. Okay, so another way of talking about esterification reactions is to call them a condensation reaction because we're producing water. Okay, so esterification reactions are known as condensation reactions. That's because a molecule of water is produced by the reaction, and you can see that here. Okay, so if I've highlighted this OH group and that H, okay, when the reaction happens, this OH and that H leave to form a molecule of water. So as the reaction's happening, you will see water coming off of the reaction. That's why they're known as condensation reactions. Okay, and in biology, you would have talked about that in the biochemistry unit. Okay, if I'm not careful, this reaction's actually under equilibrium, where there should be another arrow pointing in that direction. The water can come back into the molecule, break it apart, and then in biology, this would be called hydrolysis, where water goes into the molecule and breaks it apart. Okay, so using water to break up the ester. Okay, and that's what your stomach does. Okay, so if I had an excess of water kicking around, okay, with a lot of heat and temperature, I can push the equilibrium back, and that's what your stomach does. Your stomach has acid, your body has heat, and we have an excess of water. So when you're eating esters, you can break them apart and digest them using the hydrolysis reaction. Okay, but if I remove water, okay, if I do it in a very dry environment and I'm removing the water as the reaction's happening, I can push the reaction towards the right using Le Chatelier's principle to make that esterification happen. So you see, in organic chemistry, it's a good unit to do in the end because it covers almost everything we did and applies our knowledge of Le Chatelier's principle. All right, thank you.